This screencast covers the topic of matter, which you will find in Chapter 2 of your textbook. The objectives of the screencast are as follows. Define a chemical element and list the 4 elements, including their chemical or atomic symbols that form more than 96% of the human body. List the chemical elements that make up most of the remaining 2% of the human body. Explain how elements and atoms are related. And lastly, describe completely the structure of an atom, including all subatomic particles, their relative masses, charges, and positions in the atom. Matter is anything that has mass and takes up space. For the most part, if you can see it and touch it, it is matter. Now, matter is composed of fundamental units called elements, and these are units that cannot be broken down chemically into simpler substances. For example, here we have a molecule of water. Water, or H2O, is 2 hydrogen atoms and an oxygen atom. So we have an element oxygen and we have the element hydrogen that makes up water. We can break these bonds here between the hydrogen and oxygen to yield individual hydrogen atoms and oxygen atoms. But we could not further break down oxygen or hydrogen chemically. We could break them down atomically by splitting the atom, but you can't break hydrogen down into any other substance chemically, nor can you break oxygen down into any other substance chemically, because they are elements, and elements cannot be broken down into simpler substances. There are 91 naturally occurring elements on Earth and another 29 that have been created in laboratories. You'll find the elements listed by atomic number using their 1 to 2 letter symbols on the periodic table of elements. And you'll find the periodic table of elements on page A25 at the back of your book in Appendix E. Despite the fact that there are 91 naturally occurring elements on Earth, there are only four elements that comprise 96% of the human body. They are in descending order: oxygen, carbon, hydrogen, and nitrogen. So even though there are 91 naturally occurring elements on Earth, 4 comprise 96% of the human body. And that reflects the fact that these elements are the major components of the nutrients carbohydrates, proteins, fats and oils, and water. Of course, water is the most abundant substance in the human body, followed by proteins. And then we have some fats and oils in the human body, and then a small amount of carbohydrate. So these 4 elements making up 96% of the human body reflects the fact that they are the major components in these nutrients. Now, I want you to know that these 4 elements make up 96% of the human body. You are required to know that. Most of the elements that make up the remaining 4% are shown here. Notice that calcium and phosphorus alone account for about 3% of the human body by mass or weight. Calcium and phosphorus, of course, are major components of bones. And then the remaining elements serve various purposes: potassium, sodium, chlorine, magnesium are very important electrolytes. play a role in the production of nerve impulses as well as the contraction of muscles. Iodine is a major component of thyroid hormones. And iron, of course, is found in hemoglobin, which is found in red blood cells and is essential for the transportation of blood through the cardiovascular system. Because these elements make up a much lower composition of the human body than carbon, hydrogen, oxygen, and nitrogen, we don't have to consume as much of these nutrients in the food that we eat. These elements are commonly referred to as minerals, and they are a minor but essential component of our diets. I mentioned earlier that you have to know the 4 elements that make up 96% of the human body: carbon, hydrogen, oxygen, and nitrogen. And that is accurate. However, if you're going into some clinical career, it might be advantageous for you to know the 13 elements that make up more than 99% of the human body. And I'm going to give you a little mnemonic device that will help you commit that to memory. And it is C, Hopkins, Cafe, Mighty Good, and Naturally Clean. Those elements are carbon, hydrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, calcium, iron, magnesium, sodium, and chloride. These 13 elements make up more than 99% of the human body. That remaining 0.01% of the body is composed of these elements listed here. And because these elements are found at such low levels in the body, they're referred to as trace minerals. We have to consume them. They are essential nutrients, but only at very low levels in our diet. The bigger ones would be copper, manganese, zinc, maybe chromium, and selenium. The ones that are at extremely low levels in the body, I mean extremely low levels, would be silicon, tin, and vanadium. In fact, those are sometimes referred to as ultra trace minerals because they occur at such very low concentrations in the body. These are, again, essential nutrients. They have to be consumed, but at very, very low levels. Now that we understand what elements are and that elements compose the human body, let's look at the building blocks of those elements. And when we say building blocks, what we're referring to is what's the smallest amount of an element that you can have. Just like you can have a brick wall, that brick wall is composed of individual bricks, and elements are composed of individual units called atoms. Atoms are composed of what we call subatomic particles. An atom has a nucleus, and it's in the center of the atom, and that nucleus is composed of the subatomic particles called protons and neutrons. Now, the protons are shown here in red, the neutrons in yellow. Protons are positively charged, and that means they are attracted to negatively charged particles. And so we symbolize protons with a P superscript plus to note the positive charge. Neutrons have a neutral charge. That means they are neither attracted to positively charged particles or negatively charged particles. And we represent neutrons with an N superscript 0. So the protons and the neutrons are located centrally in the atom, which we call the nucleus. Outside of the nucleus, we have another subatomic particle called an electron. And the electrons are negatively charged, meaning that they are attracted to positively charged particles. So these electrons here are attracted to these protons in the nucleus. And again, because electrons are negatively charged, we represent them with an E superscript negative. So these electrons rotate or orbit around the nucleus, being attracted to the nucleus by the positively charged protons in the nucleus. And so they orbit around the nucleus similar to a satellite orbiting around a celestial body like the moon or the earth. Don't be confused or get too caught up in the two representations of an atom. Here we have the planetary model, which sort of represents the electrons, similar to what you might see representing the orbit of a satellite. And then here you have the orbital model, where you have what's called an electron cloud. That's just shaded in to represent the electrons. The orbital model just illustrates that we don't know at any given time where those electrons are in space out here. We just know that there's a greater probability that it'll be in some areas and a lower probability that it'll be in other areas at any given time. And so the dark shading represents the higher probability, the lighter shading represents the lower probability. I will not ask you any questions about the planetary model or orbital model. I just wanted to explain why the atoms are represented in two different ways here. What's important for you to know is where the protons are and their charge, where the neutrons are and their charge, where the electrons are and their charge. That the nucleus is composed of the positively charged protons and neutrally charged neutrons, and that the electrons are found outside the nucleus and they have a negative charge. Recall that all of the elements are represented on the periodic table. For each element, you'll see its symbol. In this case, it's C for carbon. And above the symbol is the atomic number. In this case, it is 6. And the atomic number represents the number of protons that an atom of an element contains. So all carbon atoms contain 6 protons because the atomic number of carbon is 6. Recall that elements are arranged by atomic number from left to right in the periodic table. I want to take a moment to discuss the atomic mass number, which is basically the weight of an individual atom. The atomic mass number is the sum of the protons and neutrons for a specific atom. And that is because the protons and neutrons are about the same size and weight, and electrons are many, many orders of magnitude smaller than either the neutron or the protons. So for the most part, we can just ignore the weight of electrons when we're calculating the mass or weight of an atom. So by convention, the atomic mass number is calculated by simply adding the protons and neutrons and ignoring the electrons. This slide just illustrates some examples of how the atomic mass number is calculated. Here we have carbon, 6 protons, 6 electrons, 6 neutrons. We ignore the electrons and just add our protons and neutrons for atomic mass of 12. Nitrogen, 7 protons, 7 neutrons, atomic mass of 14. Sodium, 11 protons, 12 neutrons, atomic mass of 23. And potassium with 19 protons, 20 neutrons for an atomic mass of 39. Again, just ignoring the electrons in each example. This brings us to, let's now discuss the subject of isotopes and atomic weight. Each element has a unique atomic number, that is, a unique number of protons. The atomic number for hydrogen, for example, is 1, therefore all atoms of hydrogen have 1 proton. However, you can have different atoms with different numbers of neutrons. Atoms which have the same number of protons but different numbers of neutrons are called isotopes, and you can have several isotopes of an element. In this example, we have 3 isotopes of the element hydrogen. The predominant one, the one that's like almost all naturally occurring hydrogen element, we simply call the isotope hydrogen, and has, of course, 1 proton, but no neutrons and 1 electron. The isotope deuterium, however, has, of course, 1 proton. It has to be the element hydrogen, but it has 1 neutron. And then there's tritium that, again, has 1 proton, therefore it's the element hydrogen, but it has 2 neutrons. Recall that the atomic mass number is the number of protons plus the number of neutrons. So deuterium is heavier, has a higher atomic mass than the isotope hydrogen, and tritium, which is sometimes referred to as heavy hydrogen, has an atomic mass number of 3 because it has 2 neutrons and 1 proton. So isotopes have the same number of protons but different numbers of neutrons. Therefore, they have the same atomic number but different atomic mass numbers. The atomic weight, which you see on the periodic table below the symbol, is a weighted average of the atomic masses of all the isotopes. Almost all of the naturally occurring hydrogen is in the form of a hydrogen isotope. Almost all of it, but a little bit of it is in the form of deuterium and tritium. So the weighted average is a little above the atomic mass for the isotope hydrogen. You'll run into isotopes sometimes when you read journal articles where they'll use isotopes. They'll put it in food or maybe in something that's being administered intravenously, and they're watching where that isotope goes in the human body because different scanning technologies can monitor and track that isotope. So if they're trying to see, for example, how the brain responds to certain stimuli, they may tag glucose with deuterium or tritium, and then they can see how the brain utilizes that glucose when you read a book or when you're shown scary pictures or something like that. Now let's review the learning objectives of the screencast. Define a chemical element and list the 4 elements, including their chemical symbols, that form more than 96% of the human body. List the chemical elements that make up most of the remaining 2% of the human body. Explain how elements and atoms are related. And describe completely the structure of an atom, including all subatomic particles, their relative masses, charges, and position in the atom.